I'm Brent Sanderson, and in this talk, I'll be discussing the best way to teach children and teenagers how to write code. I have a degree in computer science, and I've been a software engineer as well as a high school computer science teacher. Whether you're a parent looking for a good way to teach your own children coding, or a teacher looking to bring STEM education into your classroom, I hope this talk can give you a clear vision of attainable goals, as well as some practical first steps. I'm going to break this talk up into two main parts. The first part will cover recommended tools and software. The second will cover curriculum and teaching methodologies. Let's start with tools and software. The first choice you have to make when teaching computer science is, what language should I use? As an educator, I always start my students off with a language called Java. If you want to, you can make several philosophical language arguments in favor of or against Java, its widespread use in industry, its portability across platforms, the nature of its syntax, but ultimately, I don't think those arguments are very important. In many ways, when you're first starting, one language is as good as another. There are two big practical reasons to start with Java. If you're a school teacher, it makes sense because the AP computer science test that the College Board uses for assessment is written in Java, and you probably want your program to build towards that test. But whether you're a parent or a school teacher, there's a very compelling reason to use Java, and that's because the very best educational tool does. Which brings us to Greenfoot. Greenfoot is an open source code editor that uses the Java language. I'm confident that it's currently the best teaching tool available. It's a fantastic middle ground between a drag and drop environment like Scratch and a professional development environment like Eclipse or Visual Studio. On the right side of the screen, you can see all of the classes where our code is written. Double-click on them to view the code editor. In this project, where a hero is trying to collect coins in a maze, all of the hero class's behavior is written in Java. The only reason he can move around and run into walls and pick up coins is that the code says all of that is possible. Greenfoot provides a small library of classes and methods that a beginner can use to quickly start building very visual, interactive projects, but it's also a full Java environment. Any valid code will work and compile, and you can even import external libraries. Greenfoot also makes testing easy, allowing you to inspect an object to see the state of its variables and test the behavior of any code you've written on the fly. It provides a fun, easy way for beginners to get started writing code, but because it's a full Java editor, it can scale with them as they learn. It can be used by beginner, intermediate, and advanced level students equally well. Now that we've talked about the tooling and software, let's move on to curriculum. When I was a high school teacher, I was part of a great school and district that was willing to provide me with any curriculum resources that I wanted. Unfortunately, I soon realized that none of the existing curriculum was very good, and it wasn't adequate for my vision of what a computer science classroom could be. So out of necessity, I started writing my own. Over the years, that curriculum took the form of online courses, and I started EncodeCreate. You can find my online courses at courses.encodecreate.com. Many of our resources are completely free. Rather than walk you through a given project, because you can do that on your own, I'm going to go over many of the guiding principles that went into this curriculum's creation and talk about how you should apply those principles when teaching your child. First, engage their interest. All of these courses teach coding concepts through projects where students make their own video games. The traditional way of teaching programming is to start them in a command line interface and teach them how to print text on the screen. But that's not very fun, and if you don't grab their attention, they'll get bored quickly and be more inclined to quit the first time they get frustrated. Second, teach them that being wrong is okay. Even professional programmers make mistakes all the time. When your child first gets started, they'll probably feel very confused, and they'll have to fix a mistake every 5 minutes when their code doesn't quite do what they think it should do. That's all right. It's part of learning. All of my curriculum enforces the idea that they'll get comfortable with confusion as part of the learning process. Third, encourage them to experiment. If they're not afraid to be wrong, then they shouldn't be afraid to experiment. Once their code is working, see what happens if they change it. If they have an idea, try it out and see how it works. If it doesn't work, try to figure out why. Many online coding tools and resources are purely on-rails tutorials, and they don't allow room for experimentation. But experimenting encourages a higher level of thought and deepens understanding. Last, you should guide your child into creativity. Once they've followed directions and built a project, see if there are any new ideas or features that they want to try to implement on their own. If they've done several projects following a set curriculum, encourage them to come up with an original idea and try to build it from scratch. Once a child starts to take ownership of their own learning, their passion will grow, their effort will increase, and their learning will only accelerate. Which brings us back to Greenfoot. Not only do students have complete freedom of the code that they write, they can also add their own images and sounds to fully customize their programs. Whether they find art assets online or create them themselves, they can be creative and artistic at the same time. This brings us to the end of this talk. If you are looking to learn more about good tools, resources, and techniques to start teaching a child or teenager how to write code, I hope you got some good takeaways. If you have any questions or you'd like to speak with me further, you can send me an email at brent@encodecreate.com. Thanks for watching. And because I still have a little bit of time left in my time slot, I'm going to include a short video lesson that is part of our curriculum at EncodeCreate. This video is about how to move actors within a world. When you are on the main Greenfoot window, this rectangle represents the active world. Your active world is a certain number of pixels wide and a certain number of pixels tall. If you open the code for the world, the first line of the constructor that begins super shows you how many pixels wide and how many tall. My world is 600 wide and 400 tall, so I know from this point to this point is 600 pixels, and from this point to this point is 400 pixels. The world is an example of what we call a Cartesian plane. There are two number lines. They start at the origin in the top left, and you have an X number line that counts out our number of pixels to the right, and our Y number line that counts out our number of pixels down. So we start at X coordinate 0, Y coordinate 0, X gets bigger as we go to the right. Y gets bigger as we go down. We can look at an example that maps this to an active window. Just like our world, that's 600 wide and 400 tall. We see we start at 0, 0. Our x-axis goes all the way to 600, and our y-axis goes all the way down to 400. Let's look at some code for a helicopter. If I say set location, I can define my movement as making sure I'm always at x coordinate 100, y coordinate 100. If I go to the main window and I hit run, I will immediately move to 100, 100. If we look at our plane, we see 100, 100 is very near the top left. So that's why this code moves my helicopter to the top left. If I put a larger number for my x coordinate, if I say 450, 100, I can see if I move across to 450 and down 100, I should be at about here. If I test my code, hit run, that's where I move. If I give a larger y coordinate, so now I'm at coordinate 450, 370, 450x, 370y is about right here. If I hit run, that's where the helicopter moves. I can find my current x coordinate using getX and my current y coordinate using getY. Which will make me not move at all, because if I stay at my current x and my current y, I'm not moving. But if I take my current x coordinate and I add 5 pixels to it, every time we act, we should move 5 pixels to the right. And if I press run, I should see that that is rightward motion. This first number is my x coordinate. Remember, x is my sideways axis, left and right. If I want to move the opposite direction, I can choose -5 instead of +5. And every time I act, I will move 5 pixels left of my current location. If we click run, we see it moves to the left. If instead of side to side, we want to move the helicopter up and down, instead of changing our x coordinate, which measures left and right, we can change our y coordinate, which measures up and down. So if we go back to the code, we will get rid of this -5. And if we put our -5 after the y instead of after the x, we should see upward movement. If we do the opposite and we add instead of subtract, we move down. There's another way to move besides using set location. This circle represents the different degrees that a helicopter can face. The default of 0 is our image facing to the right. If I check my current rotation, I should see 0. As you add to your rotation, 90 degrees goes from 0 to downward. As we continue to turn, we'll hit 180, 270, and then 0 again. If instead of using set location, I say set rotation, instead of 0, 180, that should make my helicopter face the opposite way, which it does. And if I use a command called move, I can put a number in between the parentheses, and I will move in whatever direction I am currently rotating. So if my rotation is 180, this will move me at a speed of 7 pixels per act. Bigger numbers make me move faster. Smaller numbers make me move slower. If I wanted to face up, I could choose a rotation of 270. And that will move me up. If I set my rotation to my current rotation, I won't turn at all. I'll continue moving whichever way I'm facing. If we look at our circle, we see that adding to our rotation turns us clockwise. So if I add to my rotation, that will make me turn clockwise. Similarly, if I subtract, that will make me turn counterclockwise. And if you don't want to write set rotation, get rotation, you can do the same thing with the turn command. Positive numbers turn clockwise, negative numbers turn counterclockwise. And if we get rid of our move command and we just say turn, that makes us spin in place.